yeah, so my goal for this talk and the next one is for it to not be super intense and technical. So hopefully, many of you probably know a lot of what I'm about to say, but I think this will help to get us all kind of on the same page. And feel free to say something if you can't read anything I've written. I know my handwriting's amazing, but it could happen. Okay, so I want to consider f over qp a finite extension. And basically, I think everything I say should work also for local function fields, but maybe we'll focus on the p-adic case. And I want to take G over F a reductive group. So you can pick your favorite, like GLN or SO2n plus 1 or SP2n. And the coefficients of all representations will be the complex numbers. But we're not really going to use the topology of C that much, so that it's not an essential thing. Okay. And so then the key definition is that a representation pi v so the key definition is of a smooth representation. And this is that if for every vector there exists a compact open subgroup such that V is in the K invariance. Right, so this is some constraint on the representations we consider. And then further we'll say pi v is admissible if this dimension is finite for all compact open K. Okay, and then some notation is rep G is a category of smooth representation. Okay. Yeah, so one fact that is true is that is not completely obvious, that is not obvious at all, is that smooth plus irreducible implies admissible. So that is some relationship between these things. So maybe I should say if smooth plus, okay. All right, any questions so far? Okay. So the first thing I want to do is an extended example, and that's the irreducible smooth reps of GL2 QP. So maybe a lot of you are familiar with this example, but I think it's good to discuss. So what kind of things can we get? So the first thing is we can get characters. So like the norm character composed with the determinant. And then to go further, what we want to do is we want to build up representations from characters. And so how can we do that? So what I'm going to do is I'm going to draw a diagram that I'll call like the parabolic induction diagram or the Eisenstein series diagram. And probably some version of this diagram will appear 100 times in this conference. So I'll write it like this. So in this case, this BQP is the Borel subgroup of GL2, which is like the upper triangular matrices. You look perplexed, Jared. Are you okay? And then T we can think of as some two-dimensional algebraic torus, so it's like QP cross squared. And notice the way I'm drawing the maps. So there's an inclusion of the upper triangulars into the 2x2 matrices, and there's also a projection if we quotient by the unipotent radical of the upper triangular matrices, then you get this torus. There's, of course, also an embedding of the diagonal torus into the upper triangulars, but that map plays less of an important role in what we're doing here. Okay. And so then what we can do is we can take some character chi1 times chi2 of this torus, and we want to cook up some representation of GL2 in the following way. So we'll say this is the parabolic induction, and I'll write it in this way. And what it is, so I'll define it. So it's functions from, so okay, let me define the induction. What? QP. Okay, yeah, thank you. But this will, of course, work much more generally. So let me define the induction of rho. And so in this case, rho is chi1 times chi2. And so it's functions from, so of rho comma v. So functions from, oh God. Okay, we're back. So functions like this, such that f of b g equals rho of b f of g. And I want to act, so G acts on F, like by right translation. And then this is not going to be a smooth representation, so I'm going to take the smooth vectors in here, so the ones that are fixed by some compact open. Okay, and this is the parabolic induction, and so then we immediately have some more irreducibles to add to our collection. So ind b GL2 rho is irreducible unless chi1, chi2 inverse is either trivial or the norm squared. So lots of examples. Okay, and then so when you have one of these other exceptional cases, then there's actually a reducibility point. And so let's give an example of what can happen there. So if chi1 equals chi2 is trivial, then in this case you get some sequence like this. Okay, so what have I written here? So first of all, like if we stare at this induction, in this particular case where we're inducing the trivial representation, then the definition says that, that f is invariant under translation on the left by b. So actually f can be thought of as a function from g mod b to, and we're inducing the trivial representation, so that's just c. So it can be thought of functions from g mod b to c. G mod b is p1 in this case. So it's functions on p1. And, well, you can take the constant functions, and that gives you a copy of the trivial representation. So that's why in this short exact sequence here, I have a trivial representation inside the induction. And then it turns out that the quotient is irreducible, and that's what we call the Steinberg representation in this case. Right. And it turns out that this sequence is not split. So in some representation categories, you have like for finite groups, for instance, you have a semi-simple category. So, but that is not true for us. So this is a first example of that. Okay, so we're missing some examples. So what's left? So what's left is the supercuspitals. And I'll define these as basically the things that don't come from parabolic induction. So I'm going to do a slight acceleration here because I want to define supercuspitals in general. So before we were just talking about induction from this Borel subgroup, but for any parabolic subgroup and any Levy subgroup, there's a similar construction. And so we say pi is supercuspidal if the sum is 0 for all proper p and all rows. Okay, so these are exactly the things that don't live inside parabolic inductions. So you might wonder, like, well, what about this Steinberg representation? It was a quotient of an induction. But does it live inside one? Well, it turns out, yeah, you can rearrange. So if you take, instead of the trivial character, if you take the norm box times the norm inverse, then you'll get Steinberg as a sub. So Steinberg is not supercuspidal. Okay. And so what about these supercuspitals? Well, there's an expectation that maybe is known in many cases by work of a lot of people that that there's some specific compact subgroup K. Okay, so let me just write what I wanted to say. So pi or supercuspidal would be isomorphic to an induction from some representation rho of some group K tilde that is compact compact mod center. And rho is an irreducible rep of K tilde. So an example of this is
your definition is a little funny because you never said that pi is irreducible in your definition of a supercuspidal.
We don't need that, I guess, right?
But if you want this.
Okay. I mean, it's still probably fine, right? Because rho doesn't have to be irreducible. Okay, no, it might be annoying. Okay, fine. Let's say so irreducible pi is supercuspidal. Okay, good. And then maybe we'll say all supercuspidals are like sums and extensions of those or something generated by those. Yeah, thank you. Okay, so what is an example that, so what is this compact induction? So this is the F's in the induction such that F has compact support. Mod K tilde. Okay, so some example is like we can take the compact induction to GL2 QP of from GL2 ZP times the center of some representation rho tilde such that rho tilde is an extension of a cuspidal of GL2 FP. So you take a cuspidal representation of GL2 FP, you lift to GL2 ZP, and then you want to enlarge it a little bit to deal with this center. So this representation of GL2 FP of GL2 ZP has a central character, and you need to find some extension compatible with that, and then you compactly induce all the way up to GL2QP, and then if you do this correctly, you'll get a supercuspidal representation. And that's supposed to give you an idea of how these things are constructed. And then so at this point, we've finished our construction of, our discussion of all the irreducibles, smooth representations of GL2QP. So this is kind of, so you get some characters, some parabolic inductions. Maybe these are called like principal series. And then sometimes these parabolic inductions are reducible. So then you get extra things. And then finally, you get these supercuspidals that don't show up in parabolic inductions. OK. More. OK, so now I want to move to talking a bit more about this parabolic induction operation. This is kind of essential to everything we're doing here. So and the first thing I'll say is probably some people in the audience are annoyed, so I'll start by renormalizing everything. So we'll define IGP to be this parabolic induction we wrote before, but then precomposed with some twist by the half sum of the modulus character of. So this parabolic is not a unimodular group, so there's some modulus character, and we're going to twist by that before. And what we'll see is when we do this, it doesn't change a lot, but it removes a lot of annoying like twists that would show up. So this is a good thing to do. So what are some properties? So firstly, these functors are exact. And secondly, this parabolic induction takes admissibles to admissibles. And this is not true in general of compact induction. So, like in fact, what we're kind of using here is that G mod P is compact. So in general, you won't preserve admissibility, but you will for these parabolic inductions. And then IPG has a left adjoint, which is this Jacquet functor. And this is defined to be, again, a twist of some other thing. And then this so this Jacquet functor is defined such that it takes pi to, so first you restrict to p, and then you take the u coinvariance. And then that gives you a representation of M, this Levy subgroup. So, and so this is a left adjoint. And that's actually pretty easy to see. And then a much deeper fact is that there's a right adjoint. So I think the fact that there's a right adjoint is not that deep. I think the fact that we can explicitly say what it is maybe the deep part. So the right adjoint, especially since I already told you this functor was exact. So the right adjoint looks, wait, what have I written? Oh, okay, now as I get to practice using the eraser. Okay, so the right adjoint is JP op pi. So the Jacquet functor with respect to the opposite parabolic. And I think here already we need the renormalization. Like I think the twists don't match up if you don't renormalize. Okay, David says yes, so it must be true.
This is hard enough that you should say who discovered it.
Oh yeah, thank you. This is a deep result of Bernstein, whose name will appear a lot in these talks. Yeah. And then compact induction has a right adjoint, which is just like restriction. Okay. Okay, so these are my properties. Let me know if you want to go back or you have questions, or I'm not going to prompt you, I'm just expecting you to call out.
I have a question.
Good.
This, the number 4, so what exactly does it say? P, and then, is it the opposite parabolic, or what was?
It's the opposite parabolic.
Okay.
Yeah, exactly. So it's not so obvious that this is true, but it turns out to be true, and it turns out to be super useful. A lot of the things I will state later in this talk and the next actually use this fact. Others? Okay, so there's a number of dualities. Oh God. When am I supposed to go to? It's 7:56 p.m.
You have until 8:30.
8:30 p.m. Okay, good.
8:35, I guess.
Why is it every time I rest my finger on it, it's like doing this? Okay. The contragradient. So if the contragradient is, so you exactly take V dual and then you take the smooth vectors of that. So this is a smooth representation, and some fact is that pi is admissible if and only if pi dual is isomorphic to pi. Right, so the admissibility was saying something about the k fixed points is finite dimensional, and when you take a double dual of a vector space, like the finite dimensionality is quite important. So that's maybe some indication of what's going on there. And another thing is that this is true. And this again uses this renormalization. Linus, I think, claimed to me that this was like the main justification or something. So, okay.
I think the main justification is that the normalized version preserves unitary representations.
And for me, the main justification is that the normalized one is compatible with Langlands.
That too. There's 8 reasons.
But yeah, so basically you're probably realizing that it's a good idea to do this renormalizing. Okay. Fine. So these are some formal properties. The next thing I want to talk about is Hecke algebras. So if you take representations of a finite group, it's the same thing as modules over the group ring. This is an important and useful fact. We want some kind of similar result here. And so I will explain to you, and there is such a result, but it's not exactly the same because we're, of course, using infinite dimensional representations. And so I'll explain to you exactly how to state that result. So we'll define the Hecke algebra as the convolution algebra of locally constant, Pauli supported distributions on G of F. And after fixing a Haar measure, on G of F, we can identify with locally constant Pauli supported functions. The map is just kind of like F goes to F dx, where this is our Haar measure. But just be careful because these functions and distributions kind of like are opposite to each other. So if you only think of the Hecke algebra as functions, your maps might sometimes go the wrong way if you're not careful. Okay, so then something that is true is this Hecke algebra, it's an associative algebra. It's not going to be commutative. And it's also not going to have, if G is not compact, it's not going to have an identity element. So, so one useful thing is to write it. So one useful thing is to write it as a union or a limit, I guess, of what I'll write HGK, and these are K bi-invariant distributions or functions. Okay, and what I wanted to say is that this Hecke algebra has another incarnation that will be important to us. So it's the endomorphisms of this induction. Maybe there's an op here or something, but, well, okay, Dave approves. So, and one way to see this is if you write out this endomorphisms of some Hom and then you apply this adjunction that I mentioned earlier, then you'll kind of see why this is true. Okay, fine. And so if pi v is smooth, then actually this Hecke algebra acts on V by in the following way. Need a V in there. Okay, and this integral seems terrifying, but remember that this function f is locally constant, compactly supported, so actually the integral is pretty simple. It's like some finite sum. And then the theorem is that this action induces equivalence. Induces equivalence. Rep G with HG modules ND, where ND means non-degenerate. So you want the fact that you want modules that satisfy this. And if you think about what will happen in this case, like the smoothness will imply this non-degenerate property, because if you take some vector and it's in the K invariance, then when you act by like the identity function on K, you should just fix the vector. Okay, so this is the answer to my
What does it say, mod upper
ND, non-degenerate.
Oh, and that's the condition of non-degeneracy.
Yeah, that's the condition of non-degeneracy. ND.
Actually, while I have your the way you defined h of g as locally constant distributions, before you brought out the Haar measure, what did it mean for a distribution to be locally constant?
Yeah, so maybe you want me to define this in a different order or something. There is a definition for a distribution, but maybe I don't want to go into it.
I see. But there is a definition.
Yeah. You don't have to think of it as a function. Okay. All right. So the last thing I want to talk about, so I guess probably I'll finish a little bit early. That's okay. Is this homological duality. And so this uses so this is, maybe I should say Bernstein's homological duality. This uses the derived category.
Capital D.
What?
Is that a capital D?
Yeah. Right. So, and this is like, maybe I started off just thinking about rep G, but in the talks that follow, really we will want to be thinking about derived categories. Like a lot of the results that will show up in this conference don't make sense and are not true if you do not pass to the derived category. So, okay, so you might be concerned, but actually, basically everything I've said extends to the derived category. This is not going to be a big issue. So don't feel caught off guard right now. Like you can just imagine that if you have complexes, you can make sense of every construction I've said, and then everything goes through.
I think every functor you wrote down is exact, so.
Right, so.
Can I keep bothering you?
Yeah, please.
Do I have to worry about anything like, are there enough projectives in this category?
I mean, you do have to worry, but it's true, so now you can stop worrying. Okay. So I'll use this for the compact objects of this category, which apparently is the theorem of Bernstein that in our current setting, some complex A is compact. If and only if each of these representations is finitely generated, and also like we have bounded cohomological amplitude. Okay, and then for these, and then for compact pi's or complexes pi, we can define another duality deco, such that.
Sorry, so what's cohomological amplitude?
I think it just means the degrees that the cohomology can show up in.
By the way, Alexander, when you can remember, maybe you can try to repeat the question.
Oh, yeah.
Just for the recording.
So the question was, what is cohomological amplitude?
What does finitely generated mean in this context?
Just like as a module, say, over the Hecke algebra.
Because there's finitely many vectors whose G orbits generate stand as a representation.
Yeah. Okay. All right. Do I want the G there?
Yes.
Okay. Okay. And so this is a duality on D rep G compact. Okay. So a priori, this RHOM is just some complex, right? We don't know, who knows like what degree the cohomology is supported in and what it looks like. But in fact, it turns out that it's a very well-behaved thing.
Sorry, can you say a friendly sentence or two about what the hell this formula means? Like, what structure, why does this make sense?
What do you mean?
What factor are you using about H of G that makes this make sense?
That it's like a G module?
Is it just a G module, perhaps?
Perhaps it is 2G actually?
Bi-module, thank you.
Thanks.
Yeah, it has a left and a right. Okay, thank you.
But then this formula are you using, which module are you using for the G and then
So, I mean, I don't know.
So this curly H has two commuting P actions, right?
Mhm.
This Arham eats up one of them,
Yeah,
and then I guess the other one is a priori a right action, but you convert it back to a left action through inversion.
sure. Thank you. Oh, I was supposed to repeat that question.
It's okay.
Or you can summarize the conclusion, but yeah.
Anyway.
If you can.
Okay. Okay, so then the theorem is, so we want to say if pi is irreducible, we'd like to say something about what this thing is. So if pi is irreducible, then this deco pi is supported in a single degree. Which degree, you might ask? Well, come to my next talk on the Bernstein Center. But for now, let's call it d pi. And then and so then this is an honest, pi is, let's say this is an irreducible representation of rep g, then this shift now is an honest representation of rep g, and it turns out that this is also irreducible.
No minus sign.
What?
No minus sign.
Oh. Probably there will be many other sign discussions in this conference. And then, so what is the formula? So deco pi d pi is isomorphic to az pi do. So az is the Albert-Zelevinsky duality. And maybe up to some signs, this is given by the following. So you take a sum over standard levies. And you take, yeah, and so a priori this is some operation in the Grothendieck group, but then you have to actually prove that this will give you an honest representation. So like a priori it's a virtual representation, right? So what I'm doing is I'm taking pi, I'm taking the jack A down to some levy, and then I'm inducing it back up. Okay, that's something, and there's a sign. And then my claim is that all these things cancel, or they will cancel in some way. Since I claimed that if pi is irreducible, this whole thing gives you an irreducible. So example, so what if pi is supercuspidal? Well, in this case, JPG pi is 0 when p is proper. So in this case, all these terms but one will cancel, and what you're left with is just pi. So you get az pi is pi. But then in this cohomological duality, there was a contragradient. So then you'll get deco shifted of pi supercuspidal is pi contragradient. So you can tell that there has to be something like a contragradient here because this operation that I wrote down for AZ is covariant, and this deco thing is contravariant. So, okay. And then maybe another example is like in this GL2 case, what if pi is this Steinberg representation? So on the one hand, you have one term that is just Steinberg because you take P as G and then nothing happens. And then on the other hand, you have On the other hand, you have the M is just the torus. So P equals G, P equals B. And in this case, when you take this Jacobi module, you get some character, then you induce it back up, and you get some reducible thing that contains trivial and Steinberg. So in the Grothendieck group, this is like trivial plus Steinberg. But there's also a sign, and so then when you combine these things, you should get like the trivial representation, I guess. Maybe there's also a sign out front.
Oh yeah, in the definition of AZ, there's like a plus minus.
Yeah. Thank you. And so the outcome of this operation is that deco should be trivial up to a sign, which I think is maybe 1 in this case. 2? Oh yeah, 2.
Pi, or some pi. Pi.
Oh yeah, 2. You think it's plus 2 here? Okay, we can debate it.
No, it's minus 2 for sure. It's certainly minus 2.
Okay, there's disagreement. Okay, so I know it's a bit early, but maybe I'll stop here.